Hello everyone, my name is Dharya, and today we are really excited to present to you Zaplang, which is a lightweight and educational programming language that we have designed and built ex- entirely from scratch using Prolog. Our goal was to create a language that is not only fun and intuitive to use, but that also gives us deep insight into how a programming language actually works. Can we move on to the next slide? Yeah, so we had two main motivations behind this. On the educational side, we wanted to understand each component of a language pipeline, which is a tokenization, parsing, evaluation. Practically, we aim to build a fully functional interpreter with a clean and, if possible, beginner-friendly syntax and modular structure for easy debugging and testing. Next slide, please. So Zaplang supports key features you'd expect from any modern scripting language. Variables of type integer, boolean, or string. Control structures like if, else, while, for, and even ternary expressions. Expressions involving arithmetic, logic, and comparison. Simple output using print tags. Scope code blocks using curly braces. It works both on Mac and Windows, and all the source files use the .zap extension. So Zaplang is structured as a modular compiler pipeline. The tokenizer reads the source file and breaks it into a list of tokens. The parser then builds a syntax tree using R grammar rules. The verifier checks for semantic correctness like valid variable uses and structure. The evaluator finally interprets and runs the code. Everything is coordinated by the main program zap.pl, which glues the whole modules together. Now we'll move on to the execution flow. This diagram basically summarizes almost everything that I've explained so far. At the top, the execution begins with a .zap file, which is run by .sh or .bat script. The Zap helper is the orchestrator. It reads the file and directs each and every step of the pipeline. The tokenizer converts the raw code into a token list. Parser transforms the token list into a parse tree using grammar rules. Verifier checks this parse tree for correctness, valid assignments, expressions, and control flow. The evaluator runs the verified tree and generates the final output. The output is sent back through Zap helper and is printed on the screen. Each and every module is independent, making the system modular and easy to test. This flow ensures the program is parsed, verified, and executed correctly each and every time. Now we'll move on to the next slide and Arya will take over.
Hello everyone, my name is Arya and I will be starting with the grammar design of our language, which is Zaplang. For the grammar design, we have used DCG, which is definite clause grammar, in which the grammar structure is like there will be a program and a program will be a group of statements. Again, going down, a statement will be broken down into one or more statements, eventually broken down into assignments, expressions, or Boolean expressions. In the grammar, we have many data types, loops, and operators, such as we have integer, string, and Boolean data type. Moreover, we have if else and while loop. Uh, Talking about the operators, we have ternary operator and the print statements. For basic arithmetic calculations, there are arithmetic operators like addition, subtraction, multiplication, and division. To find some relational context between the operands, we have relational operators like greater than, less than, greater than, equal to, less than, equal to, and not equal to operators. And to find the logical context between the operands, logical operators like and, or, and not are present in our grammar. Uh, For the Zap helper is like a helper or a utility component which mainly acts as a coordinating hand between all the components of our project. Its entry point takes place through a zap.bat or zap.sh through this command, which is zap underscore swipl, zap underscore helper.pl. And the main purpose of zap helper is to coordinate between all the phases through a pipeline and to make orchestration between them. And also, if any issues or errors are done, to then its main feature is also to handle them and debug the final output. Yeah, next step. Now coming to the tokenization module. Tokenization is the first part of our compiler design, which mainly does the lexical analysis in the program. It takes the inputs as a .zap source code file and then gives the output in the form of stream tokens. Here, the tokens can be one of the keywords, operators, symbols, or the literals, and can also be the identifiers. Uh, and yes, if any errors are present during tokenization, it will also print out that particular error. So it does do the error handling part in that particular module also. Now coming to the parsing module, after the tokenization, the input of the stream tokens will be taken as an input by the parser, and parser here the parser will be working together with the grammar of our programming language, and by taking into consideration of that grammar, the parser will be giving an output as a parse tree. So the parse tree will help us to visualize the oral program of a oral program, and also if there are any issues, then error handling will be taken place in the parser file, and that issues will be printed out so that we can easily figure it out. So from this upcoming slide, Tejas will be taking.
Hi everyone, my name is Tejas Shah, so I'll be taking over. So compiler verifier. What it does is it ensures systematic correctness before execution and validates variable declarations and usage. So basically, what it does is check if variables are declared before use and no ensures no redeclaration of constants or integers or any issues are there. So it basically traverses the past syntax tree before evaluation and maintains all the environment of known variables. And if it fails, if it fails, it will be printed out so that the user can easily identify the issue of his Zap code. Evaluation engine. So basically, this is an compiler evaluator. It executes the past syntax tree of Zaplang, and it evaluates all the expressions which are present in the code and performs logical control flow execution. So basically, it what it does is like it uh, goes through the code and evaluates the expressions like variable assignment, conditional executions, loops, arithmetic operations, boolean logics, etc. So now I'll tell you how to run this Zaplang. So basically, our there is a if you want to run any Zaplang code, the extension is .zaplang, and we have well written documentation over our GitHub for the code. After that, if you're like running it over Mac, you can use the bash command, which is given here, dot forward slash zap dot sh data forward slash test one dot zap. If you're using Windows, you can use bat command, zap dot bat data for backward slash test one dot zap, and you will be able to see all the outputs in the terminal itself. So this is an example program. Here, what we do is we just assign variables of, like, for example, integer x is 5 is assigned to x. This string is assigned to greeting. Boolean is assigned to this variable and is active variable, and we are printing out each and every variable, and this is the output. I'll now show you the code of our compiler. So as I'm running it on my Mac, I'll be using .sh bash command. So this is the entry point of our compiler. So what it does is it listens for this command, and once this command is used, it will point to zap helper.pl. So what helper.pl will do is it is just um, a kind of function wherein it will line by line it will execute all the components like tokenizer, parser, verifier, and evaluator. And if any issue in those components, it will it will print out using catch blocks and error handling techniques. So this is the main helper, and in this SRC, we have created all the evaluator, grammar, parser, tokenizer, verifier. And right now, for testing, we have created a test1.zap in data folder. It can be anywhere in your machine. So basically, this to explain again, I'll be running this test1.zap. This is the bash command I was talking about, and once I hit enter, every output is printed. So this is the program output. As expected, it is showing the expected output. It is printing all the variables which are present in the program. So that was the example uh, of our compiler. Now Samanvita will take over.
Hi everyone. I'll be walking you through some of the key challenges we faced while building Zaplang. One of the biggest hurdles was handling the grammar complexity. Since we used DCG in Prolog, managing nested control structures and recursion while keeping the rules clean and readable took a lot of trial and error. Another tricky part was parsing ternary expressions. The operator precedence made it ambiguous at times, so we had to write additional DCG rules to ensure it was parsed and evaluated correctly. Environment management was also challenging. Inside nested scopes, it was really important to keep track of variable states. So making sure the evaluator could look up and update values properly required very careful design. Lastly, debugging in Prolog wasn't straightforward. There's no native step-by-step debugger, so we had to rely on writing statements to trace the execution and understand what was going on. To tackle these, we followed a few key resolution strategies. We tested incrementally after adding each feature, logged intermediate outputs like tokens and the environment state, and designed everything modularly so bugs could be isolated more easily. Next slide, please. And for the future scope, we have some ideas for extending Zaplan. Firstly, we want to add proper function support with parameters so that we can enable recursion and promote code reuse through modular design. We also plan to introduce advanced data types like arrays, lists, and dictionaries. This will allow for richer programs and enable things like indexing and iteration. Another area we are focusing on is better error handling. Right now, debugging can be frustrating, so we want to provide more descriptive syntax and runtime error messages, ideally with line or position indicators to make issues easier to track down. On the performance side, we are thinking about introducing an intermediate representation to make evaluation faster and improve how memory and scope resolution are handled. Uh, Finally, we would love to make this Zaplang cross-platform with smooth execution on Windows, Mac, and Linux, and eventually package it as a installer or CLI tool to make it more accessible. And for the conclusion, Zaplang is a custom-built language designed entirely in Prolog. It supports variables, conditionals, loops, ternary expressions, and output. And it's built around a clean modular pipeline from tokenizer, a parser, verifier to evaluator. We are happy about how readable and extendable the grammar is using DCG, and we think Zaplang demonstrates the full language pipeline in a very educational way. What we really learned through this project is just how powerful Prolog is, not only for parsing but also for logic-based evaluation. We also saw how crucial it is to integrate the components tightly and test frequently. Every piece from grammar to evaluation has to talk to each other seamlessly. All in all, this project gave us a deeper appreciation for language design and debugging discipline, and we are excited about how far we can take it next. So this is all about Zaplang. Thank you.